You've been presented with this circuit, so the question pops in your head: how will you solve it? Further than that, we have nodal analysis, which is a method that allows for us to find unknown voltages within the nodes of a network, being based on Kirchhoff's current law, where all current entering is equal to all current leaving a node. The method for nodal analysis can be broken up into 5 steps, being: 1. Determine the number of nodes within the network. 2. Picking a reference node and labeling each of the remaining nodes with a voltage variable. 3. Label current directions and polarities. 4. Apply Kirchhoff's current law to each non-reference node. And 5. Solve the resultant equations for the nodal voltages. Let's take a step back and apply the steps to the presented network. For step 1, we can find the nodes within the network by looking at the junctions, which are located here and here. With this in mind, for step 2, I have chosen the reference node to be here, as indicated by the ground, and have labeled the other node with the voltage variable of Vx. For step 3, the direction of current can be seen within the network, where current first heads toward the center of Vx, and then down towards the reference node, labeling I3, I2, and I1 appropriately. I have also chosen to label the voltages as they head from high to low potential, which will be important in preceding calculation. From this, we can now move on to step 4, where Kirchhoff's current law can be applied to node Vx, where we obtain the equation of I3 minus I2 minus I1 equals 0 from the application of Kirchhoff's current law, with I3 being provided by the circuit and I2 and I1 being unknown. To find these unknowns, we can apply Ohm's law as I equals V over R, where V will be the respective voltage for the current minus Vx, as it heads from high to low potential. This is then divided by the respective value of R for the current. This leaves us with I3 equals 3, I2 equals V2 minus Vx over R2, and I1 equals V1 minus Vx over R1. We can then sub them back into the original Kirchhoff's equation of I3 minus I2 minus I1 equals 0, where we can also sub in the respective values for V and R. This gives us the formula of 3 minus 6 minus Vx over 6 minus 9 minus Vx over 2. To further simplify the equation, we can multiply 3 by the value of 6 to remove the denominators. We can now conclude step 5, where rearranging the equation for Vx will provide a final value of 3.75 volts. We can further verify our calculations by substituting 3.75 for Vx into the first equation, which gives the current values of 0.375 for I2 and 2.65 for I1, where 3 minus 0.375 minus 2.65 equals 0. This agrees with Kirchhoff's current law, as I3 minus I2 minus I1 equals 0, and it can be rearranged to show that the current entering the node will equal the current leaving the node.